Today we're going to discuss the limit of a function. What is the limit of a function? The limit notation, first of all, we notate it as limit x approaches c f of x equals L. What does that mean? That means if the value of f of x is close to L whenever x is close to c. Whenever x is getting really close to the value c, the y or f of x is getting really close to L. Meaning from either side of c, the y value is getting really close to L. The limit at c has nothing to do with the value of function at c. The function may or may not be defined at the point c, but the limit might still exist. So if we look at a function graphically, I have a function here, f of x. As I'm getting closer and closer to c, on the x-axis, what y value I'm getting closer and closer to? The y value is getting closer and closer to L. And that's how we represent the limit. Limit x approaches c, f of x equals L. Again, it means as x is getting closer and closer to c, the y is getting closer and closer to L. The limit of a function can take any numeric value, including 0. The limit does not exist. The limit can be infinity. Actually, it does not exist. The same thing. It can be going to infinity. So let's see a couple of examples. So limit exists for a function if the left and right hand side limit both left and right side limit approach to the same number, then we would say the limit exists. This is regardless if the function is defined or not at that point. So here's an example. We're given a function f of x equals 1 when x is not equal to 2, f of x equals 0 when x equals 2. So this is the graph given for this function. And we want to evaluate the limit x approaches c f of x. So when x is getting really close to 2, what value does y get really close to? That's what we're looking at. So when x is getting really close to 2 from the left side and the right side, the y is still equal to 1. Notice that the function is not defined. There is a hole. The function value is not equal to 1. F of 2 is not equal to 1. Still, the limit x approaches to f of x is equal to 1. The y value is getting closer and closer to 1, or y value is equal to 1 when x is getting closer and closer to 2. Again, notice that like we just said, the function is not defined. What is f of 2 equal to? If you were to find the value of the function, f of 2 is 0 in this case. Okay, still the limit is 1. Okay, next example, find the limit of the function numerically. So numerically is when we can create a table. We can create a table coming from the left hand side and the right hand side of a particular number, and use a calculator to estimate what y value I'm getting really close to. For example, in this next limit x approaches 1, x cubed minus 1 over x minus 1, for this problem, the function is not defined at 1, right? This function is not defined at 1. The function is undefined at 1. Undefined at x equals 1, because if I plug x as 1, I will have a hole in there. In my graph, there would be a hole. So let's go ahead and think about the numbers really close to 1 from the left hand side and from the right hand side. So numbers really close to right hand side are 1.001, 1.01, 1.1, 1.25, 0.999, 0.99, 0.9, 0.75. All right, so let's go ahead and plug them into the calculator. And if I use x as 0.75, so I'm going to do f of x will be 0.75 to the third power minus 1 over 0.75 minus 1. And that's going to turn out to be 2.3125. 2.3125 and 2.71, plugging into the calculator, 2.47 and 2.99. We have 3.003, 3.03, 3.31, 3.8125. Okay, so now we want to estimate, as x is getting really close to 1, what value is y getting really, really close to? So I'm going to look at the values that are really, really close to 1. 2.993.003 looks like as x is getting really, really close to 1, the y value is getting really, really close to 3. Okay, so I'm going to say the limit x approaches 1, x cubed minus 1 over x minus 1 is equal to 3. And we can see it graphically as well. So right below, I do have a graph of this function. If you remember how to graph rational functions, go ahead and factor x cubed minus 1. It's going to be factoring into x squared plus x plus 1 divided by x minus 1, and these will cancel. There will be whole at x equals 1 and 1 and so 1 and 3. The whole would be at 1 and 3. There is the whole over here. So there's my whole in the graph. And I have graphed x squared plus x plus 1. All right, so now let's take a look. What value does y get really, really close to when x is getting really, really close to 1? Well, coming from the right hand side and coming from the left hand side, from both sides, the y value is getting closer and closer to 3. So we would say this limit x approaches 1 of x cubed minus 1 over x minus 1 is equal to 3. This limit is equal to 3. So in order for the limit to exist at a point, you must be approaching the same number coming from the left hand side and coming from the right hand side. Now we're going to talk about one-sided limits, okay? Or this would be one-sided limits. So left-hand limit, what is the left-hand limit? Left-hand limit is when I'm getting closer and closer to a particular number from left-hand side. Left-hand limit. Left-hand limit has a special notation. Limit x approaches c with the negative sign in place of the exponent, and that means I'm getting closer and closer to c from the left hand side. Okay, and that would be one-sided limit. The limit at a point may not exist, but one-sided limit may still exist. Okay, another we have the right-handed limit. Right-hand limit would be limit x approaches c with the plus sign f of x. So the plus sign tells me I'm approaching c from the right hand side. So that's the notation for the right hand limit. Okay, so limit of a function can take the following values. It can be any finite number including 0. The limit can be 0, 1, 2, 3, any negative number, any positive number, any decimal, any fraction. The limit may not exist, and we would write that does not exist when it's going to two different numbers from either side. Or it may be infinity or negative infinity. Even when it's infinity or negative infinity, we would say it does not exist because limit is the number, and that number does not exist if my y value is going to infinity. So let's take a look at some examples, the limits that do not exist. So in this example, I have the dash and dash limits are different. So in this case, limit x approaches 0, absolute value of x over x. We're using the graphical approach here. So looking at the graph, I have graph of this function, absolute value of x over x. Coming from the left-hand side, so let's go ahead and evaluate both one-sided limits. If I'm coming to this function from the left-hand side of 0, my y value is approaching to -1. And if I'm getting closer and closer to 0 from the right-hand side, limit x approaches 0 from the right hand side, absolute value of x over x, that is equal to +1. Okay, and you can see those two limits are different, so we would say the limit does not exist. You are not approaching the same y value coming from left and right hand side as x is approaching 0, so we would say this limit does not exist. Okay, next we're going to look at unbounded behavior. Unbounded behavior is where you're going to infinity. So here's graph of a function 1 over x squared. As x is approaching closer and closer to 0 from the left hand side, what is happening to the y value? Well, y value is going to positive infinity in both cases, and we can also say it does not exist. Technically, limit does not exist in this case because the limit has to be a number. Okay, next example, as I'm getting closer and closer to 0 from the left hand side, What's happening to my y values? Y values are going to negative infinity from the left side, positive infinity from the right side, and I would just say the limit does not exist. Okay, limit would be does not exist. Oscillating behavior. So in this case, as you can see, the graph oscillates between positive and negative values. It doesn't go to one particular number, as I'm getting really close to zero from the left and right hand side. So I would say again the limit does not exist, because then it's switching, oscillating between positive and negative values on the either side of zero. Next one, this one is interesting. It's oscillating, but the oscillations are getting smaller and smaller and smaller and smaller as I'm approaching zero. So because the oscillations are getting smaller and smaller, so oscillations are getting smaller and smaller, so that would mean I would have to, my limit would be zero. Okay, so oscillations are getting smaller and smaller. Oscillations are getting smaller. So this limit is going to be zero. As I'm getting really close to zero, the y value is approaching zero because the oscillations are getting smaller and smaller. So there are three ways to evaluate the limits. The first way is evaluating the limits numerically. Numerically means we are going to be making a table. So in the numerical method, we make a table by picking the x values on the left and right hand side of the c value, or the point where we're going to evaluate the limit. And we see the pattern, which y value are we approaching coming from both sides. Or we can evaluate the limit graphically. Looking at the graph, we can tell which y value are we approaching coming from left and right hand side. Or we can use algebraic method, where we use factoring, adding, subtracting, fractions, complex fractions, simplification, rationalization, and different algebraic methods to evaluate the limits. In the next video, we'll talk about how to evaluate the limits numerically, and another video on graphical method, and we'll make another video on algebraic method. That's all in this video.